Good afternoon. Today we'll explore how ABC Semi Corporation can improve spare parts stocking by leveraging data already collected in NCE tickets. Our goal is to ensure that the right parts are available when needed, reducing downtime at customer sites and supporting continuous production. We'll walk you through the current process, highlight the challenges with the traditional 98% stocked metric, and show how a data driven approach can improve readiness and decision making. Before we dive in, it is important to note that all data in this presentation is mock data created for academic purposes. ABC Semicorp is a fictional company, but its operations reflect real patterns seen in the semiconductor capital equipment industry. Quantities, lead times, and costs are illustrative. The key takeaway is that while the numbers are simulated, the challenges and our proposed solution are grounded in realistic operational scenarios. With that context in mind, let's move to our agenda and see how we've structured today's presentation. Here's a quick roadmap for our presentation. We'll start with an overview of ABC Semicorp and its spare parts process, then explain why current metric of 98% stocked can be misleading. Next, we'll introduce our proposed analytics solution, followed by data, metrics, and workflow impact. Finally, we'll discuss our experiment design and expected results. By the end, you'll see how a data driven approach can improve stocking decisions, reduce stockouts, and enhance overall tool availability.
Okay, to start off with the company background, ABC Semi Corporation is within the semiconductor industry, specifically providing equipment for chip manufacturing as well as on site engineering support for tool installation, failures, and other needs. Given the nature of production, any tool issues directly impact customer operations, and it behooves ABC Semi to provide prompt repair services. The process we'll examine today is the spare parts fulfillment process. When a part in ABC Semi's equipment fails, either during initial installation or during operation, an engineer then submits a ticket for a replacement. From there, someone verifies that the part is showing is available and routes the part to the engineer. The part's availability is displayed on the stocking list, which tracks inventory levels, including how well the overall list is doing in terms of parts availability. Altogether, the process sounds reasonable enough and should help customers reduce tool downtime, but there are inefficiencies that don't hold up to scrutiny. Today, inventory is tracked as the percentage of parts that meet required stock levels. So 98% stocked in this case does not mean 98% of maximum stocking capacity. It means 98% of tools are meeting the minimum stocking requirement on the stocking list. This process was built through analysis that not only largely excluded input from the engineers interfacing with customers, but it also doesn't incorporate real-time data. Ultimately, this means that a 98% stocked rate doesn't equal a 98% fulfillment rate if that 2% includes a commonly required or high failure tool. To dive deeper into that, the problem facing the organization is list decay. The list is only as good as its underlying data, and many entries haven't seen updates in years. Some parts may be long lead. Knowing you have a gap doesn't do much good if you have no recourse to resolve it for 6 months. Another highly troubling issue for this stocking list philosophy is that parts don't fail in a vacuum. You may have the minimum in stock for an individual part, but if there's an underlying quality control issue from a supplier for a recent batch, your stock may churn far faster than anticipated. Lastly, there's failure data being collected in relatively real time, but that information is siloed and never makes it to the team that manages the list. Together, this presents a problem where the current process provides little more than the illusion of strong procedures.
Our proposal uses existing NCE data to improve inventory decisions. Instead of reacting to failures after they happen, the system identifies high-risk parts using historical failure patterns. It also detects sudden spikes that may indicate supplier or quality issues. This creates a dynamic stocking process that updates based on real operational data. This proposal shifts inventory management from a static list to a data-driven process. Today, NCE data is collected but not actively used for stocking decisions. In the proposed model, that data supports risk scoring and inventory recommendations. The process fits into the current workflow without changing field operations or shipping activities. Our solution combines two analytical methods, risk scoring and anomaly detection. Risk scoring evaluates parts using failure history, lead time, and operational criticality. Anomaly detection identifies unusual spikes that may signal supplier or quality issues. Together, these models convert raw NCE data into clear inventory actions. Scoring model ranks parts based on operational risk. Historical failure patterns carry the highest weight because frequent failures create the greatest impact. Lead time increases risk when replacement parts are difficult to obtain. Criticality measures how essential the part is to tool operation. Temporary burst flags raise the score when sudden spikes or supplier issues occur. The anomaly detection model identifies unusual increases in part demand. This is important because defective supplier batches can create sudden failures across multiple sites. The model compares current demand against normal historical patterns to detect abnormal activity early. When an event is identified, the system can increase stock levels, trigger supplier review, and temporarily raise the part risk score.
For our analytic solution, the primary data source is an NCE ticket system, which captures every part failure across sites. Our data set includes 680 records spanning 28 sites over 24 months. We also use supporting data from the existing inventory list, including part criticality, lead times, and current stock levels. By combining these sources, we can calculate a risk score for each part and detect unusual demand spikes, allowing the spares team to make data driven stocking decisions rather than relying on static lists. To evaluate the effectiveness of our solution, we track four key metrics. The primary measure is the stockout rate, which is the percentage of requests not filled from available stock, which we expect to decrease as the gaps are identified. We also measure burst detection lag, or how quickly the system flags sudden spikes, targeting a window of 3 to 5 days. List accuracy rates tracks how current the inventory list is, aiming to increase from 58% to 95%. Finally, we monitor tool downtime caused by missing parts, which is the primary business impact metric. Our approach has minimal impact on field engineers. They continue submitting NCE tickets as usual. The main change is for the spares team, who will shift from manual list reviews to a data driven dashboard. They'll act on ranked recommendations and alerts, making specific, actionable decisions instead of relying on a single aggregate metric. Successful adoption depends on building trust in the model outputs and defining clear approval rules for updating the inventory list, ensuring that all decisions are both timely and accurate.
What this slide demonstrates is the practical output of the model. Rather than presenting raw data, the system generates a prioritized risk ranking across parts, incorporating failure frequency, lead time, and operational criticality. From that, it produces clear, actionable recommendations, whether to increase stock levels, add parts to the list, or monitor for stability. The key insight here is that several high-risk parts are currently under-prioritized in the existing system, which directly highlights gaps in the list accuracy. Additionally, anomaly detection allows us to identify burst events across sites, enabling earlier visibility into potential supplier-related issues. To evaluate the effectiveness of this approach, we propose a control comparison across sites. A control group will continue using the current static stocking process, while a treatment group will adopt model-driven recommendations. We will measure outcomes across key performance metrics, including stockout rate, detection lag for demand spikes, and order to delivery time. This structure allows us to isolate the impact of the analytical enhancement and determine whether it produces measurable operational improvements. The expectation is a reduction in stockouts and faster identification of emerging issues. There are four primary takeaways from this analysis. First, the current 98% stock metric does not reflect operational readiness as it measures the list completedness rather than alignment with demand. Second, the necessary data already exists within the NCE system but is not currently leveraged for decision making. Third, the proposed change is relatively low complexity as it integrates into the existing workflow without requiring structural disruption. Finally, the expected impact is significant, including improved inventory alignment, reduced stockouts, and more timely data-driven decisions. This concludes our briefing. Are there any questions?